the first few days of class, we've taken kind of a high-level approach, and now it's time to ease things down a little bit, and we're going to slowly start talking about Galois theory. So let me just start at the beginning in a way. So Galois, so he was studying polynomial equations. So Galois was motivated by the study of polynomial equations. I mean, here's maybe the basic question. The basic question was something like this. Given a ring R and some polynomial, let's say f of x in R bracket x, let's say it like this. So what are the nature, or what is the nature? What is the nature of the solutions to the polynomial equation f of x equals 0? Now, that's intentionally vague, but I mean, so in some sense, we're trying to figure out what can we say about the roots or the zeros of the polynomial f of x, right? So when I say what is the nature, well, okay, we got to make sense for, this is a bit vague, right? But that's kind of, that's what we ought to look at. And we'll have to make this precise as we go along. Now, the classical question, right, when they originally started studying this way back, right, is for r equal to z, right? So the classical, or let's say classically, going back even to the Greeks, the interest was when the ring of coefficients was in z, right? So studying polynomials whose coefficients were integers. Okay, so let's just look at this example now. So let's say we take the polynomial f of x. We're just going to be very simple. So let's say f of x equals, let's say x plus 2, right? Right. Thinking of this polynomial as living in z bracket x, when we look at the solution, well, we know the solution is -2, right? So I told you we were going to take things down a notch, right? So the solution to x plus 2 equals 0, we can all do this, is -2, and the point here being that the solution lives within the ring of coefficients. But if we consider the polynomial, say, so if we consider the polynomial g of x, and let's say it's 2x minus 1, right? Once again, viewing that as a polynomial in z bracket x, we have the solution to the equation 2x minus 1 equals 0 is, what was it, 1/2. And that is not within our ring of coefficients. And so, you make a little, unhappy face. What do you call that? A frowny face? Whatever. So, all right, so what? So, I mean, do we care? Well, we know, well, we're comfortable with 1/2. But this example here tells us that there is absolutely no hope. If you want to study the solutions in general to a polynomial equation of this form, there's no hope. You cannot expect, right, the solutions to live within the ring of coefficients. Okay, fine. But 1/2 is not so bad, right? I mean, where does 1/2 live? Well, it lives within the rational numbers, right? So we can say, but note that 1/2 lives in Q, and how does Q relate to Z? Well, Q is the field of quotients of Z. So, but note that 1/2 is in Q, and Q is the field of quotients of Z. So what did we have to do? We recognize that our solution does not live within Z, but by extending Z a little bit, right? By expanding. Right? So let me just this is sort of a theme that we're going to have. Extend Z, extend Z to find the roots. Right? So we have to enlarge our ring of coefficients. And more generally, if we have an integral domain, so if D is an integral domain, and f of x is in, so f of x in D bracket x has degree 1, so is linear, then the solution to the equation f of x equals 0, it may not lie in D, but it's guaranteed to lie within the field of quotients of D. So then the solution to this lies in the field of quotients, and let's use a k here, k of D. And I mean, we're studying very simple polynomials here, degree 1 polynomials, and what do we see? Well, okay, by expanding the ring to this field right here, at least you get all the roots to the degree 1 polynomials, which maybe is not that exciting, but what it does tell us is don't waste your time working with plain old integral domains. If you want to be, we might as well at least consider polynomials whose coefficients live in the field. But once again, okay, so let me, I want to put this in quotes here before I say this. So what did we need to do? We have to extend D to K to find the roots. So this also tells us, so it tells us we should study polynomials in K bracket X, where K is a field. And then we move on to the next example. Okay, so that sort of tells us everything we need to know about degree 1 polynomials. So now let's move on to the next degree. So let's look at f of x equal to x squared minus 2, and we're going to consider this viewed in a field, so we can think of this as living in Q bracket x. And well, then what? Well, this polynomial right here, so this has roots plus or minus square root of 2, which we know does not live in Q. Right? Plus or minus root 2 are not rational numbers. And so once again, what do we do? Well, if we wanted to factor this polynomial, or if we want to find the roots, one place we look, we know that these are real numbers. So we could say, but plus and minus root 2 live in R. And so once again, what do we have? We can extend Q to some bigger field, expand it to a place where we actually find the roots. So once again, we'll say, so now we extend Q to find, or to R to find the roots. Well, fine. So it's true that the roots live in R, right? The roots to this polynomial. But R is really big compared to Q. Right? And Q is countable, but R is uncountable. So somehow, I don't know. I mean, you got to do a lot of work to extend Q to R. And so, let's say, note that Q is countable, while R is uncountable. And so that somehow, I don't know, we don't like that. It seems like it's too big. And so then you might ask the question, well, can you extend Q just a little bit, not all the way to R, to some field that contains Q, and that contains Q and contains these roots right here? And the answer is yes. And so let me just say this as a fact. The set K, consisting of all objects of the form A plus B root 2, where A and B live in Q. It turns out that this is a field. You can show that K is a subfield of the real numbers, and it's countable. So this is a field. And I should say contains. So we'll say also, obviously, plus and minus root 2 live in K. And so here is, you could call this a more efficient way of expanding Q to get a place where the roots live. We can say, and, yeah, that's fine. So once again, extend Q to K to find the roots. So now let's see. I think I've done enough examples here. Here's the general question. I'm going to say this, and this is really the title of this chapter is, I think, Fields and Field Extensions or something like that. What's it called? Yeah, Fields and Field Extensions. And I haven't defined field extension, but I've used this word extend. And so this is sort of the motivation for the study of field extensions. And so the question goes like this. So given some polynomial with coefficients in a field, is there a field capital L with K contained in L that contains all the roots, or we could phrase it a little bit better, so that f of x factors, such that f of x factors in L bracket x. I mean, in all these examples, we said yes, but I somehow made a distinction between this one R and this K, and we'll say if so, can we do this efficiently? Do this. I need to put efficiently in quotes because I haven't really specified what I mean by efficiently yet. But that's the basic idea, right? If we have a polynomial, and you've seen this if you took Math 482 or whatever your ring theory class is, when you're studying polynomials, there's this question of reducibility over a field versus irreducibility. And so this falls in that same kind of category. Now, what we want to do, we want to study polynomials, and can we factor it? If we could factor it completely in L bracket x, then we'd be able to identify who the roots are, the roots of that polynomial, right? They'd all have to live in this L. So that leads us to the following definition. So, an extension of a field K is, so here's the idea. What we want, really all we want is a field that contains K. But we want to be a little bit more, we want to relax the notion of contains a bit. Okay, so this definition is going to be a little bit more than just it's a field that contains K. So an extension of a field K is a triple which we'll write as I, comma K, comma L, where L is a field, and I from K to L is a monomorphism. So in this setting, remember, monomorphism, that means one-to-one homomorphism. Here we're talking about ring homomorphism. So an extension of a field K is a triple IKL, where we have a field and a ring monomorphism from K to L. Now, when we have this, because it's a monomorphism, that means that the image of I of K, is a subfield of L. Right, so that's the end of the definition. So observe that I of K is a subfield of L, and this subfield will be isomorphic to K. So that is, that is isomorphic to K. And so this allows us then to identify, to view, right, we know that I of K and K are isomorphic. I of K is sitting inside L. And so we can identify K with L and view K as essentially sitting inside L, even though technically as set-wise, it may not be true. Right? So observe that we got a subfield that's isomorphic to K. For this reason, we can identify K with I of K. Algebraically, they're indistinguishable. And so what do I mean by identify K with I of K? That is, view K as being a subfield of L, even though technically, from a set theoretic point of view, that may not be true, right? We know that there's an isomorphic copy sitting inside L. So, from an algebraic point of view, we can, right, when we say that L is an extension of K, what we're saying is that there's an isomorphic copy of K inside L, so we might as well view it as living inside L. So there are going to be times when we really don't care about the monomorphism I. There will be other times where we do have to be specific and actually think about who this is, be specific about I. But for most purposes, we're going to just say, let's consider an extension, and we're not going to need to be specific about who this monomorphism is. We just know that there's an isomorphic copy of K sitting inside L, and so we'll think of K as a subfield of L. And the notation goes like this. So notation, what we do in most cases is we essentially disregard the I, right? So the notation is to write L colon K, and this right here means that L is an extension of K, and unless we really care, there will be certain cases where we have to be specific and refer to I explicitly, right? So we know that there is a ring monomorphism from K to L running around in the background, but we don't need to mention it in most cases. This is not the only notation for extension, so other authors use the notation L and then a diagonal slash K, but this just looks too much like a quotient. And so in this book, we use this colon notation, and that's fine. But just be aware, other authors are going to use L slash K like that. Okay, so we have this idea of extension, and we're going to make a sort of a quick digression. I just want to remind you what a vector space is. So, depending on where you took your linear algebra class, you may or may not have seen the definition put in this, or worded in this way. A vector space, I guess we can say this is a definition. And maybe I should say recall, but that's okay. So it's okay. So definition: a vector space over the field. Let's use K. So over Now remember, if you took like a Math 206 type class, right, an introduction to linear algebra, when you learn what a vector space is, it's this thing that has like 10 axioms that no one's going to remember. I always forget which the axioms are and what order they go and all that. There's too many axioms. But from a more advanced point of view, the definition actually gets a lot cleaner. So a vector space over the field K is an abelian group V together with a function or a mapping F cross V into V. This mapping is called scalar multiplication. And I don't want to use a symbol for this mapping here, so called scalar multiplication. And denoted by juxtaposition. So instead of writing some fancy symbol for this ordered pair, the output of this function is going to be something, let's say a little alpha. Oh shoot, I'm using an F, and I should be using a K right there, sorry. K cross V. called scalar multiplication and denoted by juxtaposition, right? So if I take an element alpha from here and x from here, right, I'm going to write the output of the function. I'm not going to write like f of alpha v, right? We're going to write that as alpha times v. All right, so denoted by juxtaposition. Satisfying the following axioms for all, let's say, alpha and beta in K and x and y in V. And there's going to be, rather than 10 axioms, there are going to be 4 axioms. So the first one, there's a couple of distributive type properties. So alpha times x plus y equals alpha x plus alpha y. Second one, alpha plus beta times x equals alpha x plus beta x. There's an associative type property, alpha beta x equals alpha beta x, and then you need an identity property, and that's 1x equals x. Much easier to remember 4 axioms, plus you need an abelian group and scalar multiplication. And so, I mean, if you think back to what those axioms were when you learned in Math 206, there was like a closure. There's 2 closure properties, right? It's to be closed under addition and scalar multiplication. Well, when we say abelian group, that means that we're saying it's closed under addition. And when we say a function right there, that's saying that it's closed under scalar multiplication. You get some of the axioms from the axioms of abelian group. So since we know what an abelian group is, right, we get a nice, easier, or much cleaner definition of vector space. So hopefully you've seen this definition, but if not, it's really just, it's taking all the axioms and remembering that there's already 4 axioms right there, 4 axioms to be an abelian group, right? Closure, plus closure, and then right there, there's the other axiom. So I think that gives you 10 axioms already. Now, this is the amazing part about field theory. So now, consider the extension L over K, which is how I'll normally read this. L over K is the extension. Note that L is an abelian group. L is an abelian group, right? It's a field, right? So it's an abelian group with respect to addition. And you can quickly go through and show that these 4 axioms are satisfied. So L is an abelian group, and axioms 1 through 4 are satisfied for all alpha, beta in K and x and y in L. And so this is one of the amazing facts of field theory. I'll put some stars around this statement right here. I mean, it's really just an observation. I'm not even going to label this as a theorem, right? Let's put some stars here. L is a vector space over K. Right? The vectors are the elements of L. The scalars are the elements of K. So vectors are in L and scalars are in K. So this is an amazing fact right here, even though it's actually pretty easy to verify. And what this does, it gives us all the power of linear algebra, that we get to use the power of linear algebra in the study of fields. Let's check it on how we're doing on time. Oh, we're still got lots of time. I think it's a 30, sorry. Yeah. A quick definition here, or it's really notation. So the degree of the extension L lowercase, so we're defining this term degree, is the dimension of L as a vector space over K. The dimension of L as a vector space over K. So, for example, oh, whoops, and notation. So, notation here. Put square brackets around that L colon K. This stands for the degree of the extension. All right, so this is the dimension of the vector space L, right, viewed as a K vector space. So, for example, the degree of this extension C over R, it's equal to 2. Why is that? Well, a basis can be found by just looking at a 1 and I, right? Every complex number can be written as A plus BI, where A and B are real numbers. Right? What that tells us then is that the degree of the extension is 2. Right? How do you find the dimension? Well, you produce a basis. Another example, or continuing on this example, R over Q, the degree of this extension is infinite. Why is that? Well, it's really a countability thing. So the reason R is uncountable, right? If you try to come up with a finite basis, meaning take some finite number of real numbers and do all possible linear combinations, right, where you use scalars in Q, that's always going to be a countable set, right? And so there's no way with using a finite basis to produce every real number using linear combinations from Q, and so that tells us then that the degree of this extension is infinite. Oh, here's one thing. So remember the theorem from last time? It was theorem 1.1 that told us that we're talking about the prime subfield, right? And anytime if you have a field K, it either contains it either contains a copy of ZP or a copy of Q. And so what that tells us is then that every field is an extension either of some ZP or of the rational numbers. Right, so we'll say observation by theorem 1.1, every field is an extension of ZP or of Q, which means that every field can be viewed as a vector space where the scalars either live in ZP or they live in Q. So now, given extensions, let's say we have a couple of extensions now. So given extensions let's say M over L and L over K. All right, what does this mean? We have monomorphisms. And so let me just write a little diagram here. So we have monomorphisms. So we've got K going in to L. Let's call that one little I. And then we've got L going into M. And let's call that one little j. Well, we know that the composition, right, so that would be j of I, is a monomorphism, right? Composition of monomorphisms is a monomorphism. And so, since j of I from K to M is a monomorphism, we have an extension M over K. And so then a natural question would be, all right, how do the degrees of M over L, L over K, and M over K compare? And so this is our next theorem. So theorem, this will be 1.2. This one has a name, it's called the Tower Law. And it goes like this. If, so if M over L and L over K are extensions, then the degree of M over K is equal to the degree of M over L times the degree of L over K. So there's a nice relationship between the degrees, right? It's multiplicative. Okay, so we want to prove this theorem. And I think it's safe to say that when it comes to Galois theory, this is the most heavily, by far, the most heavily used theorem in the entire class. Right? In this subject, right, this theorem is going to be used constantly. So we're going to break this into a couple of steps, so or a couple of different cases, right? The first case is when everything's finite. So if both of these are finite, and then we also want to consider the cases where one or the other is infinite, right? And show that if one or the other of these on the right hand side is infinite, then the degree on the left hand side has to be infinite also. So we first consider the case that both are finite, so that or let's just say first consider. Let me word this a little better. We first consider the finite dimensional case. So let's write. I'm gonna write the degree of M over L. Let's call that M. Yep. And the degree of L over K. Let's call that N. So what I need to do then is show that the degree of M over K is equal to M times N. Okay, well now we have bases, so let's say then we have bases. Let's say x1 over x sub m and y1 up through y sub n for m and L respectively. Where here, when I say for M, that means M as a vector space over L and L as a vector space over K. Okay, so now what I'm going to do is I'm just going to produce a basis for M as a K vector space. So, so we show that the following set actually forms a basis for M over K. So we show that the set B, and here's how we're going to construct it. We're just going to mix and match, right? Remember now, all of this stuff lives in M. So we can multiply them, right? They just live in the field. And so what I want to do is I want to consider all possible multiplications of taking some x times some y. So we show that the set B equal to x sub I, y sub j, where 1 less than or equal to I less than or equal to m, and 1 less than or equal to j less than or equal to n is a basis for M as a K vector space. And it's really just, it's just a matter of cranking it out. So let's let Z be an element of M. What I'm going to do first is show that B is a spanning set. So I need to show that Z can be expressed as a linear combination of these right here. Now, we know that x1 through xm is a basis for M over L. So we can say then there exists, what do I use, alphas? Yep. Say alpha 1 up through alpha m in L, such that Z is equal to alpha 1 x1 plus dot 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 plus alpha m x sub m. Fine. Oh, but each of these alphas lives in L, and L is a vector space over K, which means that each of these alphas can be expressed as a linear combination of the y's. So now, for each, say 1 less than or equal to, do I want to use an I or a J here? J less than or equal to M, there exists beta sub, what do I use? The first subscript is, okay, yeah, so it'll be a 1j up through beta mj in K, such that alpha j is going to be the linear combination beta 1 j y 1 plus dot 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 plus beta mj y. This should be a, that should not be an M, that should be an N right there. And then that should be an N, J, Y sub N. Okay, so now let's put all this together, and I'm totally going to run out of room. Let me erase something here. So now I'm just going to substitute, right? So now Z is equal to, so we know it's this linear combination right here, but each of the alphas can be expressed as the linear combination of the y's. So z is equal to sum, I goes from 1 to n, I equals 1 to n, beta I1 yi times x1 plus dot 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 plus sum I equals 1 to n. Hopefully you can see all these subscripts. So this is these are i's here, yi. And then we have some beta im yi x sub m. And what do we have now? I mean, notice when you distribute this, I'm not going to multiply all this out, but what do we have? We have yi's times xi's, or yi's times xj's, right? This is definitely in the span of B, and so what do we have? So therefore, span of B is equal to M, capital M. Okay, so now we need to prove linear independence. So now, suppose, and I have to just use double summation now. So sum I equals 1 to m, sum j equals 1 to n. Do I want to reverse that? No, it's fine. Gamma ij yjxi, I think is the way I want to write it. Yep, equals 0 for sum gamma ij in capital K. What we want to do, if we want to show that this set is linearly independent, then we need to show that all the gamma ij's have to equal 0. So, what? Well, we know that the collection of xi's, that's a basis, so it's linearly independent. So, so since the set x1 up through x sub m is linearly independent, we have that the sum, the inner sum right there has to be 0. So we have sum j equals 1 to n gamma ij, gamma ij yj equals 0 for each 1 less than or equal to I less than or equal to m. But the y's form a basis. Since y1 up through yn is linearly independent, we have gamma ij equals 0 for each j. Well, okay, where do the j's live? They live between 1 and n. Therefore, B is linearly independent. right? So this completes the proof in the case that everything was finite. So this completes the proof in the finite dimensional case. So now we need to look at the infinite dimensional cases. Oh, I mean, I guess I should point out the size of B. In fact, so let me actually finish off this sentence, because what did we do? We created a set that has exactly m times n elements. So we can say this completes the proof in the finite dimensional case, since the cardinality of B is exactly equal to m times n. Okay, so now if the degree of m over L is equal to infinite, or is infinite, then for any finite set capital S of m, right? Because this has infinite dimension, there is no finite spanning set, so there will always be somebody outside the span, right? So for any there exists some element, say z, in m minus the span, and I need to be a little bit specific here. This is the L span of S, right? So where we're using linear combinations, or forming linear combinations using coefficients whose scalars come from L. But K lives inside L. And so this same Z is going to be in m minus the span, the K span of S, right? I mean, if you can't get Z using coefficients in L, right, the bigger field, then you certainly can't find Z using coefficients from the smaller field. And so what does that tell us? It tells us that M does not have a finite spanning set with respect to K. So therefore, the degree of M over K is equal to infinity. And now there's one last case, and that's the case where the degree of K over L is equal to infinity. So if, I just said that backwards, if the degree of L over K is finite, so infinite. So if the degree of L over K equals infinity, but the degree of M over K is finite, then L is an infinite dimensional subspace of the finite dimensional vector space M. So of the, I shouldn't say space, I should say vector space. So of the finite dimensional vector space L. Well, of course, that's impossible, right? A subspace of a finite dimensional vector space has to have finite dimension itself. So we can say which is impossible. Okay, so that completes the proof of what is known as the Tower Law. And there's a quick corollary, and I just want to end with that corollary. Which just kind of generalizes. In fact, it's also known as the Tower Law. So corollary, I'm not even going to give this a number, right? Because we're always going to use Tower Law, or we're always going to call it Tower Law. And it goes like this. So if k n over k sub n minus 1 up through k sub 2 over k sub 1 are extensions, then the degree of k sub n over k sub 1 is going to be the product of these extensions. So this is going to be degree of k sub n over k sub n minus 1 dot 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 times the degree of k sub 2 over k sub 1. So this, it just follows directly from induction, where our previous theorem is the base case, and so this we will also refer to as the Tower law. Right? Okay, so that was that's a lot of new information, but notice we've kind of dropped things down a level. This was really at the level of Math 306 and below. So we'll work into it. This course is tough. It's got some tough theorems to digest, but I want to ease us into where we're headed now, right? And it's really just about the study of polynomial equations. And the amazing thing is that we have the power of vector spaces, right? We have all of linear algebra now to work with when we're studying extension fields. All right, so we'll see you next time.